All right, so second day of 311, or related rates. We are finally getting to the famous shadow problem. But first, the letter problem. So we've got a couple problems today that are really, really common, that you'll see a lot of, and we get to use those formulas that I had you write down, so we can kind of go back and reference some of those. So example 4, 5-meter ladder is sliding down a wall. Assume the bottom slides away from the wall at a rate of 8 meters per second. Find the velocity of the top of the ladder if the bottom is 1.5 meters from the wall at t equals 0 seconds. So we're going to set up a picture. That's always our start. That way we can get a visual, label some things, name some variables, things like that. So we've got a wall right here. We've got the ground. In this situation, you always assume that everything is ideal, like the ground is perfectly flat and the wall is perfectly level and things like that. So 5-meter ladder is sliding down a wall. So here's our ladder. Looks like this. It's ladder-like. So here's something that we do know. Remember at the beginning that I had you make sure that you're separating constant info from variable info? That ladder being 5 meters is constant info. That's not going to change. Whereas the distance from the top of the ladder to the ground is going to change as it slides. And the distance from the corner of the house to the end of the ladder is also going to change. But this ladder being 5 meters tall, not changing. That's constant info, so we can put it on our sketch and we can use it throughout the whole problem. So we've got the bottom of the ladder, top of the ladder. Let's use, like X and Y here for some measurements and put some different little bits of info on this graph. So according to what they gave us here, let's write down some info. Assume the bottom slides away from the wall at a rate of 0.8 meters per second. So this is sliding at 0.8 meters per second. We've got that going on. We're going to find the velocity at the top of the ladder at t equals 2. The bottom is 1.5 meters away from the wall. All right, so let's set up. Remember, we've always got our given information, what we need, and then an equation. Okay, so here is what we are given. What we're given is that dx by dt is 0.8. X is this distance right here, and so the distance is increasing at a rate of 0.8 meters per second, so that's dx by dt. So this is 0.8 meters per second. What we need, we want the velocity of the top of the ladder. That means we want how this thing is changing. And that would be dy by dt when t equals 2. And then we need an equation that brings all this stuff all together. Okay, so the equation that relates these three sides together is none other than the Pythagorean Theorem. So we've got x squared plus y squared equals the ladder squared, which is always 5, and so 5 squared is always 25. That's our equation. All right, so that's constant info. Make sure we are keeping that kind of separate. So here's our sidebar with all of our important information here. We'll come back to all of that in just a moment. Okay, so there's our equation. We've got everything set up. Now the next step is to take the derivative of this equation implicitly with respect to t. So the derivative of x squared is 2x, and then I include the dx by dt. It's like the chain rule piece, because it's the derivative of x with respect to t, the nested function, plus the derivative of y squared will be 2y, and then dy by dt. Then, of course, the derivative of 25 is 0. So let's isolate what we're looking for. What we are looking for is dy by dt. And now it appears that we've got a lot more information than what I originally told you we were given. We were given this, and so all we have so far is that. Now remember the tip that I've got sitting right on the screen here. Remember, there will always be a way to find all of the unknowns. All right, so here is what we need to know. We need to know what x is at t equals 2, and we need to know what y is at t equals 2. Normally, in some of the previous problems, we've just plugged in whatever this value is. Like they gave us the value of the radius at a certain time, or the height at a certain time. Well, there's no way to plug the t in, but what the t tells us is exactly where x is going to be and where y is going to be. So we're assuming that the ladder is just kind of like perfectly flush against the wall, and it's starting to slide from this point right here. We assume that it's 1.5 meters away at 0 seconds. So let's write a little side information. So at t equals 0, we know that x equals 1.5. We've got that going. And then we know the speed. And so every second, it goes another 0.8 meters. So in 2 seconds, it's going to go 1.6 meters. So at t equals 2, x is going to be 3.1 meters. It was already 1.5 meters away, which we have right here, and then its rate is 0.8. So at 1, it's another 0.8. At 2, it's another 0.8. So this is 1.5 plus 0.8 plus 0.8. So that gives us the 3.1. All right, so we've got x. We still need to find y. Well, the way we find y is by using the Pythagorean theorem. And so we use x squared, so 3.1 squared plus y squared equals 5 squared. Okay, and we just use that to solve for y. All right, so let's clean everything up. And so 3.1 squared, let's see if I have, do I really not have a calculator? All right, so 3.1 squared, just going to use my phone. So 3.1 times 3.1 is 9.61. So I subtract that from both sides. So 25 minus 9.61 gives me 15.39. That's y squared. And so then I take the square root of that. Okay, so 3.923. Okay, so now I've got x and I've got y, and I can plug those into this equation. Okay, so 2, at this particular moment, x is 3.1, and I know that dx by dt is 0.8. That was one of my given pieces, plus 2, and then I just found out that y was about 3.923, and we're trying to solve for dy by dt. All right, so just a little bit of math here, you know, some multiplication, some subtraction, some division. So what we're going to do is we're going to take this piece right here, subtract it from both sides, and then divide by this coefficient right here. Okay, so what we're going to end up with is dy by dt is approximately negative 0.632 meters per second. And the negative should make sense. What that means is that the length of y is actually shrinking as time goes on, which, like I said, should make sense. If you're taking this ladder and it's slipping down the wall, as x grows, y is going to shrink. It's not possible at all for both of them to grow unless the ladder was growing, which it's not. So that's our first one. This is a really classic Pythagorean example. Flip to the next one on the next page. We've got another classic Pythagorean example. We've got Sonia and Isaac. They're in motorboats located at the center of a lake. So we're going to start by setting up our picture, get all our labels and things like that. All right, so they are at the center of a lake right now, and then it gives them both their speeds, and it tells you the direction that they're both going in. So let's see. Sonia is traveling south, and Isaac is headed east. So let's start them right here. Sonia heads south. Isaac heads east. That's what we've got going on so far. Sonia is traveling 32 miles per hour. Isaac is traveling 27 miles per hour. And we want to know at what rate are they separating after 12 minutes. All right, so what we're looking for is this distance right here. And we'll call that r. A lot of times in Pythagorean theorem, we'll do x, y, and r. All right, so with all of these values here, let's write down what we know, what we need to know, everything like that. So the given information. The given information is that, let's say ds by dt, let's make that Sonia's distance, is 32 miles per hour. And di by dt, make that Isaac's, is 27 miles per hour. So that's the length at which this line is increasing. So this distance from here to the end of wherever their boat is, that's going to be increasing. So these are both positive values. What we need is dr by dt. How quickly this distance is changing after 12 minutes. So first of all, really quick important thing, these are both given in miles per hour, so we need to talk about hours for every time unit. So we need dr by dt at the moment when t equals 1/5 of an hour. That is 12 minutes. Okay, and then the equation that relates them all together is going to be another Pythagorean theorem, s squared plus I squared equals r squared. And here, r is constantly changing. It's not like a ladder that stays the same. Their distance is going to be growing. Okay, so there's all our info. So let's take the derivative of the Pythagorean theorem. So we've got 2s ds by dt plus 2I di by dt equals 2r dr by dt. Okay, so this one, again, there's even more information that seems to be missing. What we need is this. all we have is this and this. We don't have S, we don't have I, we don't have R, but we do know how all the variables relate to each other, and we do know how much time has supposedly passed. So after 12 minutes, let's figure out what S and I and R will be. So at t equals 12. Okay, so they started out in the exact same place. 32 miles per hour times a fifth of an hour. And Sonia will be 32 times 1/5, which let's just leave that as a nice new 32 fifths. Why not? Okay, so that is Sonia's distance. Isaac's distance is going to be pretty much the same thing. He's going 27 miles per hour. So Isaac is going to be 27 times 1/5, which is 27 fifths. And we can do decimals for those. See, 32, this would be 6 2/5, or 6.4. And then this would be 5 2/5, or 5.4. Okay, so those are how many miles they are from where they originally started. And then for the radius, we do a little Pythagorean theorem. 6.4 squared plus 5.4 squared equals r squared. At that particular moment, I did find my calculator. Oops. Okay, so 6.4 squared plus 5.4 squared equals r squared. So we take the square root of that. We get about 8.374. Okay, so we're going to plug all of those values in. So 2, S is 6.4, ds by dt is 32, plus 2, I is 5.4, di by dt is 27, equals 2, r is 8.374 times dr by dt, and that is what we're trying to solve for. All right, so we're going to add this whole left-hand side together. So we've got 2 times 6.4 times 32 plus 2 times 5.4 times 27. That's the whole left-hand side. And then I'm going to divide by the value that's attached to the dr by dt. So divided by 2 times 8.37. I'm going to use all the digits I have up above. So about 41.869. And that would also be in miles per hour. So always make sure that your answer makes sense. It definitely makes sense looking at their speeds and then knowing that hypotenuse is always going to be the largest side of a triangle. So their distance is increasing at a rate of about 42 miles per hour. Okay, hot air balloon rising vertically is tracked by an observer located 4 kilometers from the liftoff point. Okay, so let's get a nice little picture here. So here's our hot air balloon. There it is, you're welcome. So hot air balloon is tracked by an observer located 4 kilometers from the liftoff point. So here's a liftoff point. Over here, here's an observer. This is 4 kilometers. I'm really good at scaling things. At a certain moment, the angle between the observer's line of sight and the horizontal is pi/5. So we're talking about this angle right here. Since this is not constant, we're going to put a variable. 4 kilometers is constant. This guy's not moving. The liftoff point's not moving. So in our sketch, we only ever want to write the constants that stay constant. We wouldn't write the pi/5 in here because that's just an instantaneous value. It's changing at a rate of 0.2 radians per minute. So that's going to go in our given information. So what is given? Well, it's given that at a certain moment, the angle is pi/5 and it's changing at this rate. So d theta by dt at the moment, ignore that, at the moment when the angle is pi/5 equals 0.2 radians per minute. So that's the quantity that's given to us. And then what we want to know is how fast is the balloon rising at this moment. Okay, so let's use, B for balloon over here. So what we need is dB by dt at this moment. So again, at the moment when the angle is pi/5. Okay, so that's what we know. That's what we need to know. Let's tie it all together with an equation. Now, anytime that angles are involved, think SOHCAHTOA. And so what we want to do is we want to relate this angle to the information that we have. According to this angle, we've got the opposite side and the adjacent side. Opposite and adjacent should point you towards tangent. So we're going to use tangent of theta equals opposite over adjacent, or b over 4. That is our equation that we're going to be using. Okay, so there is our sidebar with all of our info, the given, the needed information, and the equation that ties those variables together. So now our next step is to implicitly differentiate both sides of this equation right here. So the derivative of tangent is secant squared. So secant squared, leave the nested function in place, then multiply by the derivative of the nested function, equals, this is technically 1/4 b, so I put a 1/4 out front, and then the derivative of b is db by dt. Okay, so what I need is this. That's what I'm trying to solve for. So you might as well multiply both sides by 4. Okay, so now that we've differentiated, now we can plug in all of the information. So 4 times secant squared of pi over 5, and then times 0.2. Okay, so we're going to get a not so nice decimal value for that. Let me show you how to carefully plug these things in. So 4 times, now remember secant squared really means you're taking the secant quantity, now plug in pi over 5, quantity squared. That's what it means to do like a trig squared value. And then times the 0.2. Okay, so about 1.222. Oops, not theta. That is, sorry. I don't know where I got that from. That is dB by dt. And if you look back for units, these units were given in kilometers, and so this has got to be kilometers. And then kilometers per minute. Okay, another one here. Indy is 6 feet tall. Here it is, the shadow problem. Indy is 6 feet tall and is walking at a rate of 3 feet per second towards a lamppost that is 18 feet tall. That's a lamppost. It's 18 feet tall. That is constant information. That lamppost is not changing sign, so I can put it right on my label. And then here's Indy. Indy is 6 feet tall. Okay, so that is also constant information. So we can put that on here. So he's walking towards the lamppost. Let's kind of put on some other side information. So now here's what happens. So this comes down something like that. Okay, so that's the triangle that we're looking at. Let's kind of label off everything that we know. He's walking at a rate of 3 feet per second towards a lamppost that's 18 feet tall. Got that. At what rate is his shadow due to the lamppost shortening? Okay, so this is a shadow over here. So here's the shadow of Indy on the ground. Okay, so that's his shadow. So we've got a couple different measurements here. So this, let's call this S for shadow. And then when he's 6 feet from the base of the lamppost, so he is walking this way. Now, let's call like this, I don't know, from here to here, we can call that like D for distance, his distance away from the lamppost. Okay, so the way we do these, and let's set up everything that we know. So the given information, what we know is that he's moving towards the lamppost at 3 feet per second. So what's actually happening is that this distance right here will be shrinking. And so the derivative of the distance with respect to time is a negative 3 feet per second. Okay, because that distance is closing up. And then what we need says at what rate is his shadow due to the lamppost. So ds by dt, derivative of the shadow with respect to time, when he is 6 feet from the base of the lamppost. So when d equals 6. Okay, so now the equation for these is a little bit tricky. When we're talking about shadows, what we actually get for the shadow problem is a similar triangle problem, because this triangle that Indy and his shadow make is similar to the triangle that the lamppost makes with these two distances. So let me show you our little similar triangles problem. I'm going to pull them out and look at them here. Okay, so this one, this is 6 feet and this is S. That's constantly changing. And then here, this is 18 feet. This is D plus S. this distance plus the shadow. Okay, so those are our two similar triangles. We can set up little ratios with them. So the equation that we're going to use is we're going to put d plus s over 18, and we know that's going to be equal to s over 16, because they're similar triangles, and so the ratios are going to be equal. Okay, so there's all our info. And so this is the equation. We're going to take the derivative of that equation with respect to time. So keep in mind that this equation is really just like a constant out in front of these variables. That will help when you're taking the derivative. Okay, so take the derivative of this entire thing with respect to time, t. So I've got a 1/18 right here. Then I take the derivative of both of these things. So derivative of d with respect to time plus the derivative of s with respect to time equals 1/6 times the derivative of s with respect to time. So we do need to simplify that up because I have two places where the ds by dt appears, and that's what I'm trying to find. So I need to get it into just one place. So what I want to do is distribute this 1/18. And then I want to subtract this term from both sides. So right now I've got 1/18 dd by dt equals, this is 1/6, we can also think of it as 3/18. So when I have 3/18 and I subtract 1/18, I have 2/18, which is 1/9. Okay, so that's my equation. So now this is what I'm trying to solve for. I plug in this value right there. So dd by dt is -3. So 1/18 times -3 equals 1/9 ds by dt. Multiply both sides by 9. And so I have this reduces to a -1/6. And then I'm going to multiply both sides by 9. And so that'll be a -9/6 or -3/2. And that will also be in feet per second. So that should make sense. The closer you are to the lamppost, the shorter your shadow is going to be. So as he walks toward the lamppost, his shadow is actually shrinking. So the shadow problem, the trick is really just similar triangles. Okay, so let's look at one more of these, the inverted cone, just so we can practice that again, because people get really weirded out with that similar triangles thing. So water is being poured into an inverted cone at a rate of 4 cubic centimeters per second. So that's a rate of change of volume. Okay, the cone has a maximum radius of 6 centimeters and a height of 30 centimeters. Okay, so that's what we know. At what rate is the height increasing when the height is 3 centimeters? Okay, so that's our needed information. We want to know how the height is changing when the height is 3 centimeters. Okay, so we can draw in here. Remember, at any given time, we've got our level of water. And so the level of water there ends up giving us a similar triangle sort of situation. So we've got, this is R, this is H. And so we know that R over H equals 6 over 30, which is 1/5. And so what that means is that the radius is always 1/5 of the height. And so we're going to make a substitution into our formula. So our equation is just the volume of a cone. And so it's 1/3 pi r squared h. But remember, we're going to make a substitution for r so we get it in terms of one variable. So 1/3 pi r squared is going to be 1/5 h quantity squared times h. So let's rewrite this one more time. So 1/5 squared gives me 1/25, and then times 1/3. So I have 1/75 pi, and then h squared times h, so h cubed. So that is my volume formula. Okay, so here's all my info. Once I get that all written out, I take the derivative of the formula with respect to t. So I've got dv by dt equals, the derivative here, the 3 comes out front, 3/75 is 1/25 pi. Power drops down to 2, and then, Oops, video cut me off again. So anyways, we're saying the dH by dt, because that's the derivative of the inside function. So remember what I need is this quantity right here. So everybody does these differently. Some people like to solve for the dH by dt before we actually plug in the info. So let me show you that once, just so you can see if that's something that appeals to you. So to get the dH by dt by itself first, what you do is you kind of divide by all this stuff. So first of all, if you're dividing by 1/25, it's the same as multiplying by 25 times the dV by dt that I have right here, and then I'm dividing by the pi and the h squared. So that's an option for you if it's something that you're interested in. So let's plug all this stuff in here. So 25, and then dV by dt is 4 centimeters cubed per second over pi, and then they said at the moment when the height is 3 centimeters. Okay, so we can simplify all this up. So 25 times 4 is 100, 9 pi. So that's our exact answer, is 100 over 9 pi. However, of course, if you're interested in an approximation, which you probably are, in case we can't think off the top of our head of what 100 divided by 9 pi is, let me plug that in. 9 pi, it's about 3.567. I'm sorry, 537. And since we're talking about the rate of change of the height, that would be in centimeters per second. Okay, and then we're going to leave that AP problem to do together.